Welcome back, focused learners. I'm absolutely thrilled to have you here for this explainer. Today, we're tackling a massive challenge that pretty much every single data scientist, statistician, and analyst faces, and that's evaluating regression models efficiently. You build a model, you feed it data, but how do you actually prove that the variables you've chosen truly deserve to be there? Well, today we're mastering the Wald test in R, and we're going to turn that statistical theory into clear, actionable code.
Okay, let's dive right into this. Which predictors in your regression model actually matter? When you're staring down a massive data set with dozens of potential variables, it's kind of like a giant puzzle. You need a reliable, mathematically sound way to prove a predictor's worth, and preferably without jumping through endless computational hoops, right? We're going to answer that exact question directly using just a single R function. So here's our roadmap for today. First, what exactly is the Wald test? Second, the math behind the test. Third, running Wald tests in R. Fourth, comparing the Wald versus likelihood ratio. And finally, reading the output and avoiding some major pitfalls. All right, moving right along into section 1, what is the Wald's test, the single model solution? By definition, the Wald test evaluates whether a regression coefficient, or even a group of coefficients, is significantly different from zero. Basically, if an estimate is far enough away from zero relative to its standard error, we can safely reject the null hypothesis that the predictor has zero effect. But I really want to emphasize the absolute magic here. It does this using only the fitted model's coefficients and their standard errors. You literally do not need to fit a completely separate, restricted model just to test a single coefficient. It's just incredibly efficient. And here's a totally surprising fact. You're probably already using it. Yep. Every single time you type summary model in your R console, look closely at that output. See that T or Z column sitting right next to your standard errors? That right there is a Wald test on a single coefficient. In fact, in a generalized linear model, that Z-value column is literally the signed square root of the individual Wald chi-squared statistic. So you've actually been reading Wald test results all along. Let's move to section 2 and see how this builds. The math behind the test. Time to look under the hood.
The formula behind this is incredibly elegant. For a single coefficient, the Wald statistic, which we call W, is calculated by taking your estimated coefficient, that's your beta hat, minus the hypothesized value, which is almost always zero. You then divide that by the coefficient's standard error and square the whole shebang. Under the null hypothesis, this follows a chi-squared distribution with 1 degree of freedom. Honestly, it's beautifully simple.
Let's actually apply that formula. If we take the classic MT-cars dataset in R and we predict miles per gallon from horsepower and weight, the horsepower coefficient is roughly negative 0.0318, and it has a standard error of 0.0090. If you run that right through our formula, we get a Wald chi-squared statistic of exactly 12.38, with a p-value of 0.00043. And guess what? If you run the automated function in R, you get that exact same number, 12.38. Doing the math manually matches R's automated output perfectly. Absolutely no magic tricks here. But doing that manual math actually teaches us a really vital lesson. Because standard error is sitting right there in the denominator of our formula, standard error inflation literally shrinks the Wald statistic. So if your standard error grows, which happens all the time with multicollinearity or small sample sizes, your Wald statistic shrinks. And that happens even if the coefficient estimate itself hasn't moved an inch. This mathematical reality can completely lead to failing to reject a null hypothesis that is actually false. You absolutely must keep an eye on your standard errors.
Okay, on to section 3, running Wald tests in R. Let's talk about choosing your function. R actually gives you 3 separate routes to run this test, and it depends entirely on your specific situation. If you're comparing 2 nested models directly, you'll want the Wald test function from the lmtest package, which is going to spit out an F statistic. Now, if you want to test specific coefficient positions without fitting a whole second model, grab wald.test from the AOD package to get a chi-squared statistic. And finally, if you have custom constraints, like testing if beta 1 equals beta 2, you're going to want linear hypothesis from the CAR package.
Let's explicitly contrast the 2 most common ones really quick, just so you firmly remember the difference. The lmtest package's Wald test compares a full model against a nested reduced model. It's absolutely perfect for asking, does dropping these variables hurt my model? On the flip side, the AOD package's wald.test looks inside just one fitted model and tests specific coefficient positions against zero. They're answering the exact same underlying question, but they approach it from completely different angles and give you different output formats.
Let's walk through the concrete steps for the nested models approach using lmtest. Step 1. Fit your full model. For example, predicting miles per gallon from displacement, horsepower, and weight. Step 2. Fit a reduced model, predicting miles per gallon only from weight. So we're dropping displacement and horsepower entirely. Step 3. Just simply run Wald Test, passing in your full model and your reduced model. When you run that exact code on the MT-CARS dataset, here's the result you get. An S statistic of 5.983 and a p-value of 0.0069. Because this p-value is well below our standard 0.05 threshold, you can confidently reject the null hypothesis. Displacement and horsepower jointly contribute significant explanatory power to a model that already contains weight. The full model genuinely, statistically, fits better.
All right, Section 4, Wald versus likelihood ratio, knowing when to switch gears.
Let's quickly compare the two. The Wald test is computationally super cheap because for a single check, it only requires fitting one full model. The likelihood ratio test, or LRT for short, requires fitting two separate models and comparing their log likelihoods, which obviously means a higher computational cost. However, think about small sample behavior for a second. The Wald test can be notoriously unreliable in small samples. The likelihood ratio test is far safer, it's more stable, and it's generally preferred when your dataset is small or when you're dealing with complex generalized linear models.
So the crucial point is this. For ordinary linear regression with normal errors, the Wald test and the F-test are actually mathematically identical. That's exactly why the lmtest package returns an F statistic by default. Honestly, just use whichever is convenient for standard linear models. But, and this is a big but, if your Wald and likelihood ratio test p-values ever land on opposite sides of 0.05 in something like a logistic regression, always trust the likelihood ratio test.
Finally, Section 5, Reading Output and Pitfalls. Let's avoid some common traps.
Here are the 4 major traps you absolutely must avoid. 1. Treating a non-significant result as definitive proof of zero effect. 2. Ignoring near-zero coefficients, which makes the Wald standard errors highly unstable. 3. Skipping your homoscedasticity check. If your residuals aren't well behaved, you've got to use robust standard errors. And 4, confusing statistical significance with practical significance. Let's look a little closer at a couple of these.
Now, what's really interesting about this first trap is just how unbelievably common it is. Failing to reject the null hypothesis, getting a high p-value, does not prove that the predictor has zero effect. It solely means your test found insufficient evidence against zero. Especially in small samples, you might simply lack the statistical power to detect a real, meaningful effect. Lack of evidence isn't evidence of lack, right?
Conversely, here's a crucial reminder. A highly significant Wald test tells you a coefficient probably isn't exactly zero, but it says absolutely nothing about whether the effect size is large enough to actually matter in the real world. A massive dataset might flag a tiny, mathematically non-zero variable as highly significant, but it might be completely useless for your actual business decision. So always check your confidence intervals right alongside your p-values. Don't just fly blind on a p-value alone. Which brings us to our final, somewhat provocative thought. The Wald test is incredibly powerful. It's fast, and it is built right into R's DNA. But its standard errors get notoriously unstable when a coefficient sits very close to zero, unpredictably inflating or deflating your test statistic. So I challenge you. Take a look at the models you're building today. Are your near-zero coefficients hiding the truth behind an unstable Wald test? Do you maybe need to switch to a likelihood ratio test? Open up your R scripts, run these functions, and put your assumptions to the test. Thank you so much for joining me to master the Wald test, and I will see you in the next explainer.